Okay. Let's go with it here. So to find where videos are located at, we're going to go to Weebly. And I can't give out the passcode. Hope I remember it myself. Okay, yes, we're in. Okay, so underneath the calculus class right over here, it just says, since we'll be meeting in person, it says all remaining videos are going to be on YouTube, and here's a link to it right here. It's just the playlist itself. Good there. Once you click on it, go to here. You should see it, and I figure I should just post all of them up there. So this is, let's see, it's the 11th, right? So this is last time's class. We finished up 2.3. 2.2, remember we had an extra little day of 2.2, 2.3. So today we should do 2.4. Hopefully Monday we'll do 2.5. We good? Okay, so there it is. So you know at least where to go, where to find stuff. Say again?
You didn't know where to find them from.
Yeah, he emailed me last night. Like 8 or 9. 8 or 9. No views, huh? That's it. I'm not going to be popular on YouTube with this for some reason. So let's go with it here. As I was doing notes for today, there's quite a few things here, so I'm going to just kind of jet into it. I figured I kind of decided last time what I'll do is I'll do lecture, and any remaining time will be for homework stuff after. But this one's going to be kind of intense here. I think we can hopefully finish in time.
Yes, we can finish.
I think so. Okay. All right. We have something called continuity, and a very huge concept in calculus. It's a continuity and the intermediate value theorem, but it just says continuity for now. And we haven't even got to calculus yet. Come on, still waiting to get to calculus here. No, we're just still doing limits and stuff. What have we been doing all this time? Yeah. Okay, let's jam. Let's move this around. Let's go to here and I'm ready. 2.4. It's continuity is the subject. I would also put and intermediate value theorem. That's what you really want to get to here. So let's go. Let's think about this here. So in calculus, what we really are looking for is something called smooth and continuous. That is like awesomeness in calculus. Smooth and continuous curve. So smooth just means it does not have any sharp corners or just corners. Don't like when tables have those either. And then also we want something called to be continuous. So we're just dealing with the continuity aspect here. And we're going to deal with it in a, how do you deal with limits and how do you define it in that sense? Okay, how do you define continuity? Technically, it's just if you could draw something. Whoa. Without lifting your pencil or pen. Okay, that's in a nutshell, that's what continuity is. If you can draw a function, whether it be a polynomial function or x squared, you can draw that without lifting your head, you're doing great. Anytime you have to lift your pencil off the sheet of paper, it just broke. We're good?
Retracting the writing part count as lifting it?
No. That's why that's.
I only asked because my sister, she gets this magazine and she had this problem where she was like, oh, can you draw like a circle or dot and then circle around the top of it and you pen off the paper? And then I did it that way, and then she said I cheated because that was what the Winter magazine told her. There's a way to do that. It's like you put the dot and then you put another paper underneath your pencil, and then you draw a circle like that. Because apparently I cheated.
Uh-huh. I don't know. We have to vote to see if he cheated, Rob. So let's go with it here. Let's go with the different continuities here. So first one is this one. I think you've seen it before. Got this little line that's usually straight. It keeps on going, and then there's one little dot right there that's just gone. That's just no fun. We call these guys removable discontinuity. All right, so that means you just have a hole there. That's it here. You've got another one, though, and I think we've seen this one before. Something like this, where you have a little skip in something. And a very, very technical math term. It's called jump continuity. Jump. Yes, my chicken scratch should be a little bit different. It seems like 2.4 in other math textbooks, continuity is pretty much spread, or in other chapter books, continuity is kind of spread throughout the book itself. This book devotes one little section to it. So it's almost like, hey, here's limits, and like, hey, here's continuity. Okay, let's keep on going. And so it has a little feel there. Okay, and one more. And you've seen this in Algebra 2, I believe, when things go like that. Remember drawing these in Algebra 2?
Yeah.
All right. So we have infinite discontinuity. Uh-huh. Just so close, yet never gets there. And one of my students in college, he did this, and he goes, this. All right. MC Hammer. Got to get at least my push to him here. Okay, so let's jam with it here. So first things first is based upon this, we've got to develop some rules with limits, obviously, that will define for us what continuity is. You good? And so there's 3 of them. I was going to make you guys discover them, but it takes a long time here. So let me just list them here. So 3 conditions. And then we'll start here. I want this box. Maybe this is a good idea. Okay. For continuity, number 1. 3 conditions. Conditions for continuity. So first things first is f of a has to be defined. It has to be a point on the graph somewhere where f of a is. The limit as x goes to a of x has to exist as opposed to non-exist. Remember, that means from the right and from the left, it's the same, right? And number 3, let's combine these guys together. The limit as x goes to a of f of x is equal to I'll be good there with those three. Let's see. And every single point along the line, if those fulfill it, we've got continuity everywhere. So think about, yeah, so let's go. Just a quick little illustration, of course. So I have just a general function like this, right? If I were to measure like, hey, that's A. I'll say, okay, is that true there? Does f of A exist? Absolutely, it's right there, right? Does the limit from the right side and left side go to that guy? Yeah. And is the limit A itself? Yeah, true. Good, it's continuous at A. Then you move on to the next one. You say, is that true over here? Right? Yes, again, it's true. So notice it has to be true at every single point. We don't ever do that. We just say, look, this is the condition. Let's see if it breaks it. So let's go with the breaking of conditions here. So exercise 1. Following. Continuous. Classify. Discontinuity, oh boy, a whole bunch of English words here. Okay, so determine that the following is continuous. If not, classify the discontinuity, which one of those three over there, and then also state which rule it breaks out of those three. So let's go first one here. Let's go like f of x is equal to x squared plus 5x plus 6. All right, so what we should be thinking about is, think about it back to Algebra 2, Algebra 1. Question is, can I graph this guy? What does the graph look like of this? Generally speaking, not exactly perfect. But isn't this guy a parabola? Yeah. And then what do you guys know about parabola from Algebra 2? The domain is from? Absolutely, sure. And the parabola goes down, right, for a little while, then it shoots back up. So is this continuous or discontinuous? It's continuous. Yeah, you can graph this guy without lifting your pencil. No problem. Okay, so that was cool. That was easy enough. Let's go to rational function. Let's go to something that looks like this. And absolutely, if you want to graph it on your calculator, that's fine too. Absolutely. If you want to graph view of it, if you just want to think about it here. All right, so I'm thinking to myself that Eli has a graph of it, is that right? Eli's graph goes something like this. Yep, and right at 3, does it have a little anything funny on your graph? No, dumb calculators. They don't know. Because at 2.9, everything's fine, right? 2.999, everything's fine, right? But right at 3, we got ourselves a little problem. Doesn't matter because you don't deal with the trig function, so you're fine. Okay, good, yeah. So we do that, yeah.
In this case, if you put 3 and 9 on the bottom.
Perfect, yeah. So notice.
So if you're trying to do that so much time, then
Okay, perfect. So we got to do 3 things here. So this guy, tell me if you guys agree this is the same thing as this. True or not true? And everybody says like this. Everybody says, no, that's not the same. No. That is not the same thing as that. Now in algebra, when we simplify things, it did simplify to that. But the functions are not the same because this one says x plus 3 with the little caveat that there's no thing that equals 3. We good? 3 is not defined. Are we good? So you guys have a graph that looks like this on your sheet of paper or on your calculator, right? Right at 3, you should have a little hole and then it keeps on going. That's what it should be. Yep, that's what I say. It's not as smart as us yet. Now, when AI starts. Your horizontal is way, way big, spread out, and then your vertical is, so take a look at your window. Your windows went from like negative 10 to 10 horizontally, but negative 3 to 3 vertically, that's why. Are we good there now? Okay, so this is discontinuity. There it is, it's discontinuous. Which kind is it? Perfect, okay, so how about this? How about we're gonna go with removable discontinuity? Let's go back to your little chart of 3 over here, these little guys. There's names for them right here. Removable is the first one.
It does have undefined.
What? Okay. Oh, when you trace it, obviously.
My calculator isn't.
Okay. Are you okay with removable discontinuity? Cool. And then which rule does it break?
The first,
The number 1 rule, yeah. So f of a is not defined. Okay, we're good there with those guys.
So you include removable and then the rule.
Second, Steve?
You would write removable and then the rule.
Correct, yeah. Removable, and then this is the rule that it breaks. Or I could say breaks rule number 1 if you want to. Okay, are we good there? So let's go on next one, C. C is f of x. The x plus 1, this would be 2 for x greater than equal to 0, and x greater than 0. So kind of tough. Now, Enrique's calculator, is it smart enough to graph piecewise functions or no?
It might be able to, but I don't think I know how to graph.
Okay. Okay, let's go for it here.
But don't we know
There's people you have to jump on.
Yeah.
Oh, awesome. Maybe, maybe not. We'll see in just a second here. Love it when I break assumptions sometimes.
It's plus 1.
X plus 1 is, this is 1 over 1, this is slope, right? So if we start off at 1, 0, it'd be like right here, right? So anything below this, tell me if you guys agree, it would have been like this, is that right? And including that, so it would have been, talk to me, does that make sense? X plus 1 is just a linear function, right? Slope is 1, y-intercept is 1. So you just go backwards from x equals 0. Then after that, it jumps to 2. So the open dot looks like, and it's going to be a horizontal line that way. We good? So, jump continuity, yeah, discontinuity.
Jump discontinuity.
Yes. So let's see. Which one does it fail? The second one, yeah, fails this one. So I'm not sure if the book, if it just says number 2 or it says limit as x approaches a.
Number 2 is not very specific. 2.
Number 2. Okay, are we good there? Okay, so let's see. That one. Let's go to the next one here. So what makes, you guys remember graphing these guys in algebra 2? These guys are also rational functions, weren't they? But the only change was the fact that this. Let me just change it up just a little bit. That's all. X minus 2. All right, are we good there? So looking at this one, I just changed that to a 2 instead of a 3. It does not factor anymore, is that right? So you don't, yeah, you can't get that x minus 2 factor out of there anymore. So at this point, I know what's going to happen is that at 2, we're just going to have something that looks like this. Is that right? Cool. Okay. So discontinuous, this has to be infinite. Discontinuity. And it kind of goes back to the first one here, right? Right at 2, f of 2 is not defined. We can say that. We can say, can we say the second one as well? This one actually breaks a lot of the laws here. The limit does not exist because the limit goes 2 different directions. And obviously, if one of the first 2 are broken, the third one has to be broken. Okay, are we good there? So that one. The difference between the infinite one and the one that's the removable, they're both going to be rational functions. Just one can be reduced, one can't. That's kind of the issue there.
Oh, because everything includes, like, if you can't factor it out, the problem part out, then it's infinite. But
Yeah, because it goes to this right here. This is what happens as you approach 2 from the, I don't know, from the left-hand side or right-hand side, whatever it is. 2 goes into here. This one's going to be coming closer and closer to 0. This is limit is going to 0. But the limit on top, we usually say k or negative k. I think we've seen these before in the limits, right? The k is not 1, so you have something that's on top that's not 0 and something on the bottom that's 0. At that point, you have a number that maybe looks like this.
okay,
Right.
because, so for the other one, you could have done the limit of it because it is simplifiable. So you could have found the limit, it would have found a limit, right?
Oh, which one?
Like the one that was the removable.
Yes, the removable.
You could have found the limit, but this one you can't find the limit. Well,
The limit is not defined.
yeah.
Yeah, because you have an infinite. You have one going plus, one going negative, and therefore you can't. Okay, we good there? Okay, let's take a look at what Sadie was saying about the fact that if you have a piecewise function, it may or should not have. And then how about this one? Here's a piecewise function for you. Yours to graph that one. We've been dealing with this one a lot. Didn't we see this one yesterday or on Monday?
Yeah.
Didn't we see this one last week Wednesday and then last week Monday as well? That's become our favorite. All right, you talk to me here. If it's discontinuity, so take a look at a graph. Take a look at that little one.
The label like not on 0. Or does it have like 1 and 1? Yeah.
So yeah, this guy here, yeah. So what does a graph look like? I think it goes like this. Is that right?
Yeah.
A little bit higher here because one is like this, hits here, and then goes like this, and then kind of gets lower and lower. Is that right? Cool. Okay, it's not defined at 0, so there should be a hole there. Except the one thing is, here's your fill out of the hole, right? They fill out with the little dot itself. We're good there. So, is f of a defined? F of 1 defined. Yeah, it's just 1. Or F of 0. F of 0 is 1. Ah, sorry. That's what I'm getting mixed up. Is that a whole bunch better? I had a 1 here.
Oh, I
It should be
had assumed you're.
1 x is equal to 0. There we go. Let's unconfuse.
That's kind of lame. It seems like a piecewise function didn't work. I guess it's. Yeah. Those are always thought we would have had a problem with.
Uh-huh. I think we're good. Is that right? I think it's continuous right there. So piecewise functions can be, as long as we kind of put them together so that they're good. As long as they're connected one to the other. So if I were to do this one, go back. If I were to place this at 1 right here, right? Then that would be continuous, right? I jumped it to 2 and just made a jump continuity here. So
Piecewise functions can be presented.
Depends where
Wait a
one
minute.
finishes and the other one starts.
But wouldn't that be like kind of the pointy?
Ah, good. So today we're dealing with just continuity only. In calculus, we deal with smooth and continuous, right? So you don't have the little corner
We
there.
haven't gotten to these yet.
Correct. Yeah. And the reason why we need it is because we can take derivatives of the function itself at all those points. If it's not smooth or if it's not continuous, then we can't take a derivative at that point. What we do is we usually break them up for those intervals. Let's break up the intervals here, then we'll break up the intervals here. Yeah, for certain type, for certain pieces here. Okay. So then let's flip the other direction on our homework here. So exercise 2. And let's see if we can get some theorems out of this here. So state which intervals the function is continuous. So let's go the other way. You know, it's interesting. Teaching out of this book here this year, it's almost like it's so slow paced. Almost it doesn't get to it. Hopefully it'll pick up as soon as we get to chapter 3. Because I like calculus when it's like, oh yeah, look at this. This is so cool. So let's do this one. So give me the interval where this guy's going to be continuous. Now, the exact other focus is give me the portions that are good. So yeah, let's go with it. So we can simplify, or we can at least factor this out, right? X gets factored out, x plus 2 gets factored out. So it looks like the interval, if they want an interval, it's going to go from negative infinity up to negative 2. You got to write that one first. We good there? And then let's see if it does union markers or is just a. It just says commas in there, but technically it should be. So union, negative to 0, and then 0 to positive infinity. There's my interval. That's cool. So hold on though. We were talking about this here. So we look at it. Is it continuous everywhere else? Yes, right? It's those little pieces there that are problems, right? So for rational functions, so we had our first sort of theorem out of this here. Theorem 2.8 in your textbook here. So it just says this, that rational, yeah, we could do that here. So rational and polynomial functions are continuous on their domain. Right? As long as So these guys match pretty easily here. So domain and discontinuity match up perfectly. So for polynomial functions, because they're continuous everywhere, their domain is everywhere. That means they are continuous everywhere. For rational functions, their domains are those little pieces of removable discontinuities. Everywhere else, they're just fine.
Sorry, does that say continuous in?
Continuous on their intervals, on their domain.
No.
Thank you. Okay, next one. Let's take a look at this one. Let's see. What's special about this guy here? How about let's put this in and let's put this in.
Just one for everything except 2. And negative.
So remember, yeah, maybe this is the distinction between continuity and domain. Is continuity is, remember, putting your pencil down. You could put your pencil down at 2. We good, and then draw it out. That'll be fine, right? You just can't go be putting your pencil down, lifting it, and then putting your pencil down again and going. We good? That's the issue there.
Could it be anything bigger than 2? If you have 3, then you have a negative. So, or yeah, that's the other. Or then just like 1, like 0, 1.
Talk to me. Yeah. It's going to go, because it's a negative there, right? You know it's flipped down. Is that right? So you have, see if this makes sense, or can you guys graph this right here, a negative x squared plus 4? You guys know what the graph of that looks like?
That's upside down.
It's upside down.
4.
It's upside down because it is a negative in front, right? That little 4 means it's stacked 4 units higher, right? So it looks like this. And then the square root function, that's another problem, right? So we have 2 problems on our hands, right? The domain of our polynomial was just fine. It was the domain of this little guy that was the problem now. So we've got a square root function. So this guy's only going to function right here. Okay, are we good? This is usually called a composite function. Now there's kind of 2 things that are playing out here, right? We've got a polynomial that's inside that function, right? We've got a square root on the outside. So we call it a composite function in the end here. And so what we do is we have to limit the domain of our function right here. So the domain is limited to -2 to +2. Everybody agreed there? Because of the square root function. But then once that is done, once the limit is done, we look at our polynomial function. We say it's continuous everywhere, right? So we say that composite functions, they limit their domain. They limit the continuity based upon their domain. We're good? Okay, so there's that one. And now let's take a look at some trig functions here. Okay, are we good with that? Does that make sense there? Just because you have a polynomial function doesn't mean it's all great and dandy. It could be something else there. Okay, so how about trig functions? And we'll finish with that here. We'll get to intermediate value theorem. Evaluate this guy. Limit as x goes to pi/2 cosine. You think so? Question is, can we plug it in? Absolutely, we can plug it in. So we can plug it in, you just plug it in. Pi over 2 minus pi over 2, cosine of 0, and the answer is just 1. Perfect. Okay. When we understand this, notice that what we're doing is we're extending out the angle measurement away, right? So we're actually sliding it horizontally to the right or to the left. It really doesn't matter. But notice there are kind of two different functions here. This is that composite function issue. So I am taking my x and I'm subtracting pi over 2 from it. That's a subtraction function. It's a linear function, right? Then I'm taking a cosine function off of that too. And so what we see here is this whole concept of domain here is from negative infinity to positive infinity. Cosine, what's the domain for cosine? Same, it's also negative infinity to positive infinity, right? Okay, so I have the inside function, no barriers to my domain, we good? The outside function called the cosine function, also no barriers to my domain. And so we can take this and we can figure out the values of those, no problem here. And so, how about this? We're gonna do theorem. Did I label this one? I know, hold on, I missed this. This should have been 2.9 about the composite function, so T 2.9. Let me write out, just so we have all of them in front of us here. Let's see, this is the way the book writes it here. It says if f of x is continuous, and the limit as x goes to a of g of x is L. Bless you. Let's get to this little piece there. So let's do, so f of the limit of, as x goes to a of g of x is f of L.
What's L? Is this a constant?
L is just a limit that you get.
Oh.
Yeah.
So,
Wait, the limit of what? The limit of f of x or g? G of x equals L. I see. Okay.
that's the same like what you told us was the word.
That is saying, sorry, guys, real quick here. On the next one, so we have a cosine function that's technically f of x. Cosine of x, is that continuous function? I think that's a continuous function, right? If that is a continuous function, is there a limit? Let's do it on the next slide here. Is there a limit inside the function? And if that's the case, we could just do the limit inside the function only. So here's how it works. Sorry, guys, I was going back and forth here. This one right here. So here's where it works, is the fact that I'm trying to find the limit of this whole piece here.
Oh, so you're gonna do the domain of the inside system? Is that what you're saying?
So cosine is a continuous function. Continuous everywhere, that's great. If that's the case, instead of thinking about the limit of this whole big piece here, what I do is I just think about the limit of that inside piece. And so if we want to do it this way, and we say, I'm going to look at the list, I'm going to look at the cosine limit as x goes to pi over 2 of x minus pi over 2. We good there? That I could plug in, right? If I can plug it in, that goes to 0. And what I could do is then I could just take the limit as cosine is at 0, which is 1. Good. So it allows us to plug in even into a composite function.
Why did you put that theorem on the previous?
I don't know because I was confused.
So but for,
So this does not belong to that, sorry. This belongs to the cosine function.
so for the problem B, you put together on that page, is that just sort of the same as the theorem 2.8 with the rational polynomial function with the domain? Because you said a composite function limit is based on the domain. Our problems A and our exercise 2, numbers A and B, both talking about the theorem with rational polynomial functions continuous on the domain.
Yes, correct. A and B are for that one. And also knowing the composite issue that comes around. The theorem 2.9 is now dealing with the cosine problem, the fact that we can do limits inside functions themselves.
Okay.
Okay, we're good there. Slowly. We're getting there. This is no fun. I want to get to calculus here. Once we get to chapter 3, hopefully it's going to liven up. This is kind of like the pre-introductory.
Have you looked at chapter 3 yet?
2.5, I glanced at it a little bit here, but I think I'm going to do kind of like my own versions of the lectures, that are the way they've presented it. Let's get through this section and the next section. Promise you it'll get better.
Do you want to switch back to the last section?
Sure.
Or the
The last slide.
Okay, this one, I'm going to connect this one here. So the book says that we have to put this theorem together here. So trig functions are continuous on their domains as well. The only issue with trig functions I'm thinking like chapter 3. Okay, are we good there? So same as rational trig function. Sure. So notice that, let's go back in our minds here. If you were to give me this right, what's the limit as x goes to 0, right, of a function that looks like this? Remember what we did is we were able to move the limit into across plus signs and minus signs, right? We're able to break it down to all the way to the last bit and then plug it in. And so I could go limit as x goes to 0 of x squared plus 5 limit as x goes to 0 of x plus limit as x goes to 0 of 3, right? I can break it up into small little minute pieces here. And so what this right here says, theorem 2.9 was the fact that I could take limits of, it's cosine of something else, right? It's a cosine of another function. And the other function is x minus pi over 2. And so what I can do is I'm allowed to move the limit into that function there. Once I find a limit there, what I could do is I could just take the value, the outside cosine value of that function, and be done. Does that help? Okay, a little bit, maybe. Okay. Let's do just a little bit of fun stuff here. So the question is this: can we prove that cosine of x is continuous? So instead of finding the discontinuities, we're going to do a formal proof saying, yes, cosine is continuous all the time. So technically what we have to prove is this. We have to prove that the limit as x goes to a of cosine of x is going to be cosine of a at every single point. So one little interesting thing is I have an a there, right? X is going to a. Then I have an a at the end. So let's do this. Let's start on the left-hand side, like we normally start a trig. I'm going to prove this. It eventually gets us all the way to here. So if I take a limit, it gets me to the a value itself. All right, one little small trick, and we have it done. The limit as x goes to a of cosine of x minus a plus a. That's my little trick. So when I put an a and a minus a, do I change anything? Cool, okay. So now, let's go limit as x goes to a of cosine of x minus a plus a. A little nuance change there. I want to put a parenthesis here on x minus a. I think we're good. Anybody remember the addition formula for cosine? Oh man, that's been a long time. That's been like a year ago for some, 2 years for others. Whew. Let's see, I think I still have to do limit here. Limit as x. Oh, that's perfect. That's close. That's for sine. I think cosine goes like this. It says cosine of your first one. In fact, let me write it up here, and then you guys finish off the problem right here. It's cosine of alpha plus beta. Gets me cosine alpha, cosine beta minus sine alpha sine beta. Can you apply that little rule to our problem here? So this one's the first function, so I got myself, I think, cosine of x minus a. Then it'd be cosine of a itself, is that right? My second function? Minus x minus a, perfect. And sine of a, there it is. I think I got all my parentheses straightened out, I do. All right, and the composite function allows me to enter this limit into here, is that right? And eventually also into here. So I could break this up. I'm going to have to do the limit of this whole thing. So if I'm going to put each individual pieces inside here, I would go cosine of x minus a. Do I have a multiplication property for limits? Ooh, gotta go back to our little notes over here. Remember when we had those little 2.2, I'm gonna find it. Basic rules for limits, I think it was called, right? Come on, I'll find it somewhere here. 2.2, that was 2.3, that's right. Oh yes, okay, you guys remember these little limit laws right over here? All right, we have a, let's see, addition, subtraction, constant multiplier. Oh, we do have a product rule, quotient, power law for limits, and then a root law for limits. And so we have that, and that we just made. We're going to use those here. So I'm going to use it, and I'm going to move it to each one of those pieces here. So cosine of a minus, It's the limit as x goes to a sine of x minus a, as well as the limit as x goes to a of sine of a. Almost done, almost done. Lots of writing. So this little piece right here, right, I could still bring that limit also into the function itself. So can I plug in an a? I think so. But notice when you plug in the a, we're doing this little rule, the fact that technically there's kind of like two things happen. I'm taking this limit and I'm putting it actually into here, right? That's kind of what I'm talking about when you talk about the composite function, right? You put the limit there. So this is cosine of 0. And this is just cosine a, right? So there's no x in here whatsoever. It's just going to be a. Limit as sine goes in there. This is going to be sine of 0. Sine a, okay. All right, help me out here. Cosine 0 is? 1 is perfect. Cosine a plus sine of 0. Zero. Sine of a. All right, the sine goes away. And I'm left with this. That is cool. So guys, real quick here, we have proved a continuity of a trig function from negative infinity to positive infinity. There it is. Cosine is now a continuous function, and we have proved it. Let's see, do we have enough time to prove sine? What did I say?
This is the same thing.
Similar, yeah.
With the others. Interesting.
That one's done,
I'll let you guys try it here on your, if you have nothing else to do this weekend.
Oh, I'm sure we will.
Limit as x goes to 0 sine of x, because that's all you need to prove. Is you need to prove that. Right there. If you can prove it, you've proved that sine is continuous everywhere. Okay, let's jam to, let's see, 15 more minutes left. Let's jam to the intermediate value theorem. That's the next thing sort of put together. Yeah, just prove it if you have time and if you want to. Very similar. Okay, guys, real quick, with limits, you know, you're kind of getting the basic stuff here, and I know this chapter 2 is kind of just throwing different things at you. Hopefully it's going to be all put together once we get to chapter 3. All right, the other one that we're going to throw at you is the intermediate value theorem. And we'll come back to it all the way probably in chapter 4, and we're going to be doing derivatives, and we're going to do applying derivatives to situations. At that point, we're going to come back to it like, oh yeah, no, that could be possible, and then we can do that. So first of all, definition real quick here. If f is continuous, it has to be continuous. Notice a lot of these a lot of theorems in mathematics is based upon conditions here. And so this one definitely. So f is continuous, a function over the interval from a to b. And you got this little z that is somewhere in the range of, let's see if it's, let me just see if it's a bracket or parenthesis here.
Is that an and between the brackets?
And, yeah, that's my little and. And I have this. Z is some kind of element. It's going to a number between f of a and f of b, if that's true, there exists number C.
Is that an E or a T between the E?
This guy is a E, is like a funny looking E. It's just rounded like this, and it means element. It's a math symbol, so it's really not equivalent. Meaning like it's inside there. So I would say this here. I would say 5 is an element of odd numbers. Good there, or on a die. So 5 is an element of, and then you can actually give me, if you have a dice or a die, you would say that right there. 5 is an element somewhere in that list. And we'll see why this is so important when we get to chapter 4. And I think the problem is a police officer trying to determine how fast a car was going. Like, yes, you did speed. Okay, are we good with the element thing, Majiggy? So let's go with the graph, because the graph looks like a lot better here when you see it here. So I got this right here. I got a function. I got a here. I got a b here. And this function could go any direction. It doesn't really matter which way it goes. But let me, just for simplicity's sake, let's go like this.
Is it part of the theorem? Yeah.
This is just a drawing of the theorem, so we can understand it. So if that's a, tell me if you guys agree, this is f of a. Funny looking f, but it is. This is b. I take it here. I take it across. This is f of b. And we just said z is somewhere here. Z is somewhere between a and b already or as a function. So if we go backwards, we can find a c. There has to be a c that's in between a and b that gives you a z value between the f of a and the f of b. That's all it's saying.
You can just look at the graph and know, like, of course, when you have a C somewhere.
Sure. So a graph, technically, so when you look at a graph, it's not provable. You're just like, oh, that's cool, right?
Your eyes could be.
Like you could have holes there that are not there. And then what happens is you take algebra and you do a proof of it. And when you have a proof of it and it's accepted, it becomes a theorem, especially when it leads to other things in mathematics. And so, I promise it will get less boring once we hit chapter 3, guys. 2 minutes. Okay. Okay, so let's do this here. Let's prove one little thing based upon the intermediate value theorem. So it says that if we have something in the range, we can find something in the domain here. Is this exercise 4, I believe? Let's do this. This will be show that x minus cosine of x has at least 1, 0 in the interval from 0 to pi over 2. Brackets here. So what this means is it's called existence theorems. You know that something exists. You may not know what the answer is, but you know it's there. That's the whole point of the intermediate value theorem. So I have a function I'm trying to figure out if I have a 0 and I'm looking just in the interval from 0 to pi over 2. So the question is there, do I know for certain? How do we find out? Like, we're going to use the intermediate value theorem, but what are we going to do? How do we find out?
Well, this domain we're looking in is 0 to pi over 2, right?
Uh-huh.
So we know we're looking for 0 in that range.
Yeah, we look at 0 in the range.
So f of 0, where that occurs.
Not necessarily, because we're talking about somewhere in that domain we're going to find it, right? Not necessarily there.
Wouldn't we put, 0 for f, or put 0 and then try to solve it?
Okay.
So isn't that right?
Because then you would have negative x equals negative.
But f of 0 is not the answer, though, right?
No, I think, well, the f of 0 is where.
No, not that one.
Oh, okay, sorry.
Like,
What?
try to solve, like, for the y value, put 0 and try to solve it.
Oh, got it, okay. So that would be if we want to solve it. The question beforehand is, does it even exist? Do I even want to solve it? That's the question. There should be an easier way to do it, right?
I mean, if we solve it in the orthogonal or
Well, let's see. Let's try it. We have some time. If I did this, yeah, if I try to solve it, is that true? Now I have myself a little problem. I have an x that's outside of a trig function, right? I have an x that's inside a trig function, and now I'm having some trouble.
I forgot the
Yeah, because then I would have what? I'd have this, and if I take the inverse of cosine, then it gets me this, and I'm stuck still, right?
You just go back and forth.
Yep. Okay, so I don't want to solve it, but I do want to know that does it exist? Is it true that it exists? And
So you have to find
something about intermediate value theorem, yeah.
between 0 is between two values, if we know that those two values exist within that, then you can know what those are.
I think so, yeah. So real quick here, Sadie's got it here. We got to find two values that 0 would exist between. I don't know, 0 divides what two values? -1 and 1, or actually negatives and positives, right? Would you guys agree that if
Oh, yeah.
I was in the negative range and I wanted to go to the positive range, I would have to hit 0 somewhere along the range? Yeah. Cool, okay, let's do this here. Let's see. If I plug in a 0, I wonder if that's going to give me a positive or a negative value. A 1, okay. So plug in 0 in here, that's going to be 0. Cool, okay, so now my question is, if I plug in pi over 2, will I get a positive value? That's all I care for, right? Because then I know I'm going to get a 0 somewhere between there. Okay, perfect. I love when numbers work out nice. Pi over 2 is a positive number? 1.5, blah, 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 1.6? Perfect, okay, so by IVT, intermediate value theorem. All right, there is a C in zero to pi over 2 that C is equal to 0. I know it exists, I know it's there, but as far as finding it, that may be even more of a problem.
Intermediate value theorem doesn't help you find it. It just helps you figure out if it exists.
Correct.
Well, it helps you know it's between the intervals, so it's more safe than having anywhere in the whole thing, but, you know.
Yeah,
It's not exactly.
Yeah, at least it lets you hone down on the interval as well. So then if we wanted to put pi over 4 into here, right, we can actually get it, squeeze it down a little bit here, right? And then we may not be able to find it here. Okay, are we good there? So talk to me, guys. Boring or overwhelming? Which one of the two? Chapter 2 is. Okay, you said overwhelming a little bit? Okay. Or okay. Sorry, I should have mentioned like, okay, it's cool. It's
but
cool.
I feel like I will be more excited when I see the relevance.
Okay.
Yeah,
Yeah.
that.
Uh-huh.
It's not like super duper engaging.
It isn't, yeah. Sorry, guys. I feel the same way. It is not engaging as well. So hopefully chapter 3 will be a lot better. And we can kind of put this limit stuff together and see where it connects. And then after that, we'll start application questions like, oh, that's how it applies to stuff. Okay, with that, we are done for the day.
Are we done with,